So, last week we were discussing about resistance, resistivity and effect of or effect on resistance and resistivity of temperature. So, this is what we have completed. This week we will be talking about circuits, right. So, last class what we did, we talk about series and parallel combination of resistors. So, when resistors are connected in series, we learn that we need to add resistance. We can directly apply the formula R is equal to R1 plus R2 plus R3 up to Rn. Okay, that was for series combination if n resistors are connected in series. Then we derive formula for parallel combination, and it was like all the resistors connected in parallel. Then parallel combination formula was 1 upon R is equal to 1 upon R1 plus 1 upon R2 up to 1 upon Rn. So, based on this one we discuss few problems, and I told you that for a simple circuit, like first thing we need to see is the series parallel combination. So, most of the time you will get the series parallel combination in one go, but in case you are not getting any series parallel combination and you are getting a conducting wire, then we can use the concept of conducting wire and we can simplify the circuit. Sometime what happens ki we do not have any series parallel combination directly and we do not have any conducting wire connected across two terminal in the circuit. Then in such type or such cases what we do, we go for other circuit reduction techniques, right. So, what are they, that we will see in today's class. Okay. Before getting into that, let us see one concept related to series and parallel combination. So, we know that if we are changing the temperature of this resistor, then this R1 will be changing with temperature, R2 will be changing with temperature. What will be the response of equivalent resistance to the change of temperature when two resistors are connected in series and two resistors are connected in parallel? Let us see that. So, based on that, there is one example, you can read the question. So, according to the question, two resistors with temperature coefficient of resistance alpha 1 and alpha 2. So, we have got two resistors having temperature coefficient alpha 1, alpha 2, and at 0 degree centigrade their resistors R01 and R02. Find the temperature coefficient of the compound resistor when two are connected in series, first part, and in parallel, second part. Okay. So, we want to find out alpha equivalent. So, two resistors when connected in series, then we know what is the equivalent resistance. R is equal to, or R equivalent is equal to R1 plus R2. Okay. So, we can substitute value of R1 as a function of temperature using this R01. I can write R01 1 plus alpha 1, for first one it is alpha 1 T plus R02 1 plus alpha 2 T. This way I can write. Okay. And here R equivalent can be written R not equivalent resistance at 0 degree centigrade, 1 plus alpha equivalent T must be equal to R01 1 plus alpha 1 T plus R02 1 plus alpha 2 T. So, at 0 degree centigrade R0 equivalent will be equal to R0 1 plus R0 2. So, that term will get cancelled out, 1 1 1, that term will get cancelled out. What you are left with, alpha equivalent is equal to alpha 1 R0 1 plus alpha 2 R0 2 divided by this R equivalent will come in denominator. R equivalent at 0 degree centigrade will be R naught 1 plus R naught 2. So, I am substituting this value over here, R naught 1 plus R naught 2. So, this is what you are going to get in first part, right. So, alpha equivalent of this combination means I want to replace these two resistor by a single resistor R equivalent. What would be the alpha equivalent for this arrangement? This way I can calculate. Same procedure I can use for parallel combination. Look at this one. For parallel combination, formula is 1 upon R1 plus 1 upon R2. So, parallel combination will be something like this, two resistors connected in parallel, R1, R2, and what I want to do, I want to replace them by a single resistor, that is R equivalent. So, for this situation I can apply formula of R equivalent. 1 upon R equivalent will be equal to 1 upon R1 plus 1 upon R2. This can be written 1 upon R naught 1, 1 plus alpha 1t plus 1 upon R naught 2, 1 plus alpha 2t. Okay, and this, if we simplify this, in place of this one I can write 1 upon R naught equivalent 1 plus alpha equivalent t. Okay, I hope you are understanding what I am writing. Now, as alpha is small, I can get this term up, right. So, this term, if you look at this term, this will become 1 plus alpha 1 t to the power minus 1. When this term goes up, it will become power minus 1, and as alpha is very small, like alpha value will be 10 to minus 3, minus 4, like that is very small as compared to 1, and temperature hardly will be changing 10 degree centigrade, 20 degree centigrade. So, this value will be very small as compared to 1. So, if this value is very small as compared to 1, I can use binomial approximation, get this power in the front. So, this will become minus, right. So, if I simplify, I can write the same expression as this term will go up, 1 minus alpha equivalent t divided by R naught equivalent, and here this will be 1 upon R naught 1, 1 minus alpha 1 t plus 1 minus alpha 2 t R naught 2. Okay, and again 1 upon R equivalent will be equal to 1 upon R1 plus 1 upon R2, that term will get cancelled out, and if you simplify, you can see this term will appear here and this term will appear here. Okay, so if I simplify, then from here I will get alpha equivalent is equal to alpha 1 R naught 2, alpha 2 R naught 1 divided by R naught 1 plus R naught 2. This is you are going to get. So, there is a small difference in this one. Here alpha 1 R1 is coming and then alpha 2 R2 is coming, while in this case alpha 1 R2 is coming and alpha 2 R1 is coming. Okay. So, I hope this whole thing is clear. So, when two resistors are connected in series and parallel, alpha equivalent what we are getting, we have calculated, and this is the way we find alpha equivalent for series and parallel combination. Okay. So, what I was saying, that alpha 1 you are getting for series combination, for this combination you are going to get this, while for this combination this was R1, R2, R1, R2. Okay. So, these are the corresponding value of alpha equivalent first case and second case, right. So, this whole concept is clear. So, temperature dependence of or temperature dependence of resistor, resistivity, we can use this concept. Now series parallel, we know how to solve the question. Conducting wire, now we know how to solve the question. In case we are not getting any of these two, then we go for Wheatstone bridge. What is Wheatstone bridge? Let's see. So Wheatstone bridge. So if resistors are connected this way, this is called Wheatstone bridge, and Wheatstone bridge is called in balance state when there is no flow of current through this resistor. So if there is no flow of current through this resistor, no current flow through R3, then it is called balanced Wheatstone bridge. Okay. For this to happen, the potential here and potential here must be same, because current flows due to potential difference, and if there is no potential difference, there won't be any flow of current. Okay. So a Wheatstone bridge is called a balanced one when there is no flow of current through this resistor. Now I want to find out the condition for that. What should be the relation between R2, R1, R5, R4, so that there is no flow of current through this R3. Okay. So I can redraw the circuit. As there is no flow of current through this resistor, I can remove this resistor because there is no use of this resistor in the circuit, no current is flowing. So circuit will become something like this. If circuit is something like this, that means current is flowing from here, whatever current flowing, let that be I1, same current will flow through this one, I1, and whatsoever be the current here, same will be current here, I2. Okay. What would be the value of this I1? I want to find out the condition. Okay. So ultimately what I need to do is potential at 2 is same as potential at 3. I can write, because I cannot calculate the value of potential, but I can easily get the value of potential difference. So this difference I can calculate and this difference I can calculate. What is this difference? From here, if I subtract V1, V1 minus V2, V1 minus V3. Okay. So if I substitute the value of potential, I can get the condition. Okay. What is the potential difference here? Current into resistance, and how much would be the current? If I connect V volt battery here, this way, so say we have connected V volt battery, look at this branch, voltage drop across this branch is V, divide by resistance will give you current. So first I will write the current. Current is V divided by R1 plus R2. If this I1 current I multiply to resistance, I will get the potential difference, V is equal to IR. So here I will multiply this to R1. Same way I can write here. First calculate current I2. I2 will be equal to V divided by R4 plus R5, and then multiply to this resistor R4. In that VV will get cancelled out. Potential will get cancelled out, and if I simplify, what I am getting is R1 divided by R4 is equal to R2 divided by R5. And rearranging this, I can also write, R1 divided by R2 will be equal to, I will get this term here, if R1 divided by R4 is equal to R2 divided by R5, then this Wheatstone will be in balance state. This one upon this one is equal to this one upon this one, then it is in balance state. Or I can say this one upon this one, R1 upon R4 will be equal to R2 upon R5. This one upon this one, this one upon this one will be equal to this one upon this one. So, if the ratio here is same as the ratio here, then there is no flow of current. So, this is the condition for Wheatstone bridge to be in balance state. Okay. Now, so we got the condition. Anywhere if circuit is something like this and we are getting this condition, then we can remove the resistor, and after removing resistor you can easily see series parallel combination and you can simplify. This is one of the use. Another use is we will be using concept of Wheatstone bridge and meter bridge and potentiometer. Okay, so this concept we will talk later, or this application we will talk later, but for time being, so instead of the way here it is drawn, it might be given this way. Here this G is representing galvanometer, later we will talk about that. So if there is no flow of current through galvanometer, this Ig is 0, Ig I am calling galvanometer current. For this to happen, this P upon R, this P divided by R will be equal to Q divided by S. If this condition is met, then there is no flow of current here. So this is another way of drawing Wheatstone bridge. Similarly, look at this one. Here, if I consider this as A terminal and this as B terminal, right, and I open this one and take it out. So here I will see galvanometer, these two came out, okay, this is P, this is R, this one is Q, and say this one is S, and across AB cell is connected. Cell is connected here. Again, if this one upon this one is equal to this one upon this one, there is no flow of current through this branch. Okay, so current through this branch has to be 0 for P upon R is equal to Q upon S. Okay. So it might be drawn this way also. You have to just check whether the ratio here is same as the ratio here. Okay. So now let us see one example, then it will be more clear. Look at this diagram. If I leave this 4 ohm and just focus on this part of the circuit, just focus on this part of the circuit, this one upon this one is equal to this one upon this one, 2 by 2 1 is equal to 2 by 2, right. That means there is no flow of current through this resistor. I can remove that middle one, I can remove this resistor. If I remove this resistor and redraw the circuit, what I can see is this 2 ohm and this 2 ohm, and then 1 2 ohm here, and then in the last we have 4 ohm. As you can see that these two are connected in series. This is 4 ohm, 4 ohm, this 4 and this 4, all are 4, they are connected in parallel. So its resistance will become 4 by 3, right. So its resistance R equivalent AB will be 4/3 ohm. So here I use the concept of Wheatstone bridge. I remove this part and we have resistor. So if you just see series parallel combination, we are not getting any series parallel here, and there is no conducting wire connected between two junctions, right. So first step we cannot use, second step we cannot use, or first method we cannot use, second method we cannot use. The third method, Wheatstone bridge, works perfectly for this situation. After removal of this one, I start seeing series parallel combination and I can reduce the circuits. I hope this application part is clear. Let us see some other examples. So series parallel, conducting wire, Wheatstone bridge we have seen. What if we have such type of circuit, right? So here we do not have series parallel combination, we do not have Wheatstone bridge over here, and conducting wire between two junction is also not there. Then we go for fourth reduction technique, that is circuit symmetry. So there are two types of symmetry. One is input output symmetry, another is folding symmetry. Okay. So what is input output symmetry? Whatever circuit you are seeing from this side, if the same circuit you see from other side, then this is called input output symmetry. Okay. So right now it is having input output symmetry. To have clarity, I will change some value. If I say instead of this being R, it is 2R. Now circuit is not having input output symmetry, because from this side you can see 2R and R, and from this side you will see R and R. So circuit is not having input output symmetry. But if I make it R, then circuit whatever I see from A side, same is circuit from B side. Okay. So what is the help we get if we have this type of circuit? So in input output symmetry we talk about current division. So our focus will be on how current is getting divided into in the circuit, that we focus on. So if I say some I1 current goes to this branch, as circuit is input out or circuit is having input output symmetry, this will deliver back I current or I1 current, because similar to the branch what we have here, because circuit is having input output symmetry, this branch is same as this branch, right. So whatever it takes, it will deliver back. Similarly whatever it takes, let that be I2, that will be delivered by okay. So if this current goes from here to here, and we have a division over here, then this current cannot be equal to this current. If some part of this I2 goes here, then this cannot be equal to this. So for this to be equal to this, as they have input output symmetry, there should not be any division here. So I hope you understood. If there is no division, what I can do, I can open this junction this way, right. So this part I will open, they are touching each other, but they are not exchanging current. As they are not exchanging current, I can open this part. Now if I can open this one, focus on this part. Now I can see these two in series, then with this one it is parallel, this will be 2R and R parallel, 2R by 3, okay. So this whole branch will be 2R by 3. So this 2R by 3, I will draw it this way, this R this one is 2R. So this is a circuit we are getting, and we can further simplify. 2R by 3 plus R, 5R by 3, 5R by 3 plus R, 8R by 3. So this upper branch I can replace by a single resistor 8R by 3, and this is 2R, and they are connected in parallel combination, right. So here I can apply formula for parallel combination. 8R by 3 into 2R, 8R by 3 into 2R divided by 8R by 3 plus 2R. This is R equivalent across these 2 points. So I can also write RAB, and here you can see we are getting 16, and here we are getting 14. So 16 R by 14, that is 7R by 8R by 7. So R equivalent of this circuit will be 8R by 7, okay. So I hope how to reduce circuit after seeing symmetry, first part is clear, okay. So if circuit is having input output symmetry, then our focus will be on current division, how current is getting divided. So once we have current division, we will come to know which junction can be open or which resistor can be removed. After deciding that, we can reduce the circuit and we will get the answer. So sometime instead of input output symmetry, there might be another kind of symmetry. Let us see the next one, that is called folding symmetry, okay. What is the meaning of folding symmetry? So if this is input terminal A, output terminal B, so we are going to get or going to connect battery across AB. So battery will be connected this way. So from A to B, if you look at, I can draw a line about which whatever I observe above it, same thing I am observing below it. So this is having folding symmetry about this line. You can fold, they are like mirror image. So mirror image of this one is here, mirror image of this one is here. Now circuit is symmetric about this. So this is symmetry, this is the way you have to check symmetry. Now how to apply the concept? In folding symmetry, our focus will be on voltage division. So focus is on voltage division. above this line we have terminal here and below this line we have terminal here. As circuit is having folding symmetry, whatever current that flows here, same current will be flowing here. If I call it I1, this will be I1 because circuit is having folding symmetry. What is happening above the line of symmetry, same thing will be happening below the line of symmetry, right. So, something like this it will be, and here through this one, this current is say something I2, we do not know. As this resistor is this same as this resistor and this current is same as this current, this potential difference will be same as this potential difference. That means this potential will be equal to this potential. So, above line of symmetry whatever junction we have and the below line of symmetry whatever junction we have, they will have the same potential, right. Similarly, if I look at this branch, so current here will be same as current here, current into resistance will give you potential difference, current into resistance will give you potential difference. So, here and here potential difference will be same. That means here and here potential has to be same, okay. So, this part is clear. Now, let us call it something C. So, as here and here potential same, I will call it C also, and this is having or this is D, this will also be called D because they have the same potential, and this junction I will call it E. So, from A to B through C and D, okay. A to B through C D and E. So, all the points I am drawing on a straight line. Let us connect all the resistors between two junction, between A and C, this R over, between A and C one more R, between C and E and C and E, between C and E R, and then one more R, these two over. Then A to E directly we have one resistor, okay. From this A to E we have one resistor. So, this intermediate one is a whole over C to D and this C to D, two resistors C to D, okay. So, C to D, this is C and this is D. So, I will connect one resistor this way and one more resistor this way, okay. So, C to D over. Now, E to D and E to D. D to B, D to B. And then the last one E to B. Okay. Now, these two are in parallel, these two are in parallel, these two are in parallel, parallel. I start seeing series parallel combination. One more thing I am able to see is this circuit is having input output symmetry, right. Whatever we have this from this side, same thing we have from this side. Okay. So, circuit is having input output symmetry. Whatever current is given to this branch, that will be written by this branch. If this current is same as this current, that means there is no flow of current here. If there is no flow of current here, I can open the junction. Okay. So, I can draw it this way, I can draw it this way. So, we can redraw the circuit. This way finally we have the circuit, and let us start reducing it. R by 2, R by 2, R by 2, R by 2. Okay. So, all these can be removed and replaced by a single resistor. R by 2, R by 2, R by 2, and then R by 2. Okay. And this will also be R by 2. Later I will connect it. And then these two resistors can be replaced by one resistor of resistance, again R by 2. So, here this R by 2, this R by 2 will make it R. Okay. R here. Now, this R by 2 and R, they are in parallel combination. R into R by 2 divided by R plus R by 2. So, this will give you R by 3. So, this can be replaced by single resistor of resistance R by 3. Okay. So, this is now R by 3, and the below one you can see this R and this R, this will make it 2R. So, now I will connect it in different diagram. So, between A and B I can see this branch. So, R, this 2 will make it R, R plus R by 3, 4R by 3. So, this is 4R by 3 and this one is 2R. They are connected in parallel. So, 4R by 3 into 2R divided by 4R by 3 plus 2R. So, what we are getting? This is 8, 3 will get cancelled out, and this is 10. Okay. So, 8R by 10 I can see, that means 4R by 5. Okay. So, this will be So, I hope you understood the procedure. If we have folding symmetry, whatever we are having circuit below, same circuit above, we start reducing the circuit and then we can simplify and find out the R equivalent of the circuit. So, these are the two basic circuit symmetric technique which you will be using frequently. Okay. When series parallel combination is not there, conducting wire is not there, Wheatstone bridge we are not getting, and we are getting circuit symmetry. So, either we have to focus on current division or voltage division. One more thing, in a circuit there might be more than one symmetry, like in this case you can see there is input output as well as folding symmetry. So, it is your choice whether you want to go by input output symmetry or folding symmetry, you are going to get same answer. Let us check. So, if I want to solve the circuit by input output symmetry, okay. So, just now I told whatever the current here, same will be the current here, because input output here it will be same as here, and this will directly go. If this is directly going, no current division, this I can open and this I can open, okay. Now this upper part 2R and R, 2R by 3. So this will be 2R by 3, 2R by 3 plus R, 5R by 3 plus R, 8R by 3. So this whole upper branch will be 8R by 3, right, 8R by 3. Similarly this whole branch, that will also be 8R by 3. Upper 8R by 3, lower 8R by 3, that means in parallel combination that will become 4R by 3. So I can draw A to B this as 4R by 3, and then this is 2R, okay. And these two I can connect in parallel. Eight I can see here, and then 10 I can see here, 10R by or 8R by 10. So 4R by 5. So as you can see that I solved the same problem by two methods, right, folding symmetry as well as input output symmetry. I am getting same answer 4R by 3. So by which method it will become simple, that depends on the problem, right. So you have to solve a problem by what method, that will come from practice. So more and more practice you have, by seeing circuit only you will be able to decide that this particular circuit can be easily solved by the input output symmetry or by folding symmetry, okay. So we will discuss more problem on this input output and folding symmetry. Let us see another one. So this is same as the previous one. If you look at, okay, if you look at this problem and you see next problem, they both are almost similar, okay. So across AB I want to find out resistance. Here I can see these two are in series, then parallel. So this whole thing will become 2R by 3, right. So 2R into R divided by 2R plus R, 2R by 3. Similarly here this is 2R by 3, this is 2R by 3, okay. And I can draw a simple diagram. And as I already told you, this current will be equal to this current, input output symmetry. Here I can open the junction. So when I open the junction, here these two are connected in series. This is R by 2. Similarly this will be R by 2. This is 2R. and I can easily see parallel series. So, this 2R by 3 and R by 2 in parallel will make it this is 2R, and here this is 4 and 3 7, right. So, 2R by 7, right. Only this part I am talking about. 2R by 3 and R by 2, they are in parallel. 2R by 3 into R by 2 divided by 2R by 3 plus R by 2. So, here 6 and 6 will get cancelled out. Here there will be 7, 4 plus 3 7, and then this will be, in that I need to add in series, this will become 4R by 3. So, 2R by 7 plus 4R by 3, okay, this will be for whole branch, upper branch. 6 and 28, that means it will be 36 and 28 will make it 34. 34 R divided by, this will be 21, okay, upper part over. Same you will get for lower part. So, lower part this and this, that means it will be 17 divided by 21 here. So, this upper one, okay, let us draw another circuit. So, I will draw separate circuit for this whole upper part. So, 34 by 21 and 34 by 21 will give you 17R by 21, and then this one is 2R, and these two are connected in parallel. 17R by 21 if I simplify, then here I am getting 34, okay, here I am getting 34, and then in denominator I am getting, if you multiply, this will become 22 and plus 17, okay, and this is 9 and this is 39, okay, this will be, this if you multiply, this you will get 42 sorry, by C calculation, this will be 42 plus 17 I need to do, 42 plus 17, this will be 9 and this will be 59. So, this I can write 59R. So, this way I can simplify, and after simplification, here this circuit is same as the previous one, only difference is earlier here we had R, now that R will be 2R by 3, okay. So, 2R by 3, this branch I connected, 2R by 3, this whole branch I have connected here, and 2R by 3 here, okay, and then this, oh, this, these two are connected in series, right. So, this is 2R, there is writing mistake here. Okay, let us check answer once. this if I look at, so 2R by 3 into 2R divided by 2R by 3 plus 2R. So 4 I can see here and 8 I can see, right? 4 I can see here and then 8 I can see. So R by 2 I can see. So this whole thing is R by 2. Okay. This R by 2, this R by 2 and this 4R by 3. 4R by 3 plus R by 2. So here we are getting 8, 11 R by 6. Okay. So this whole upper branch is 11 R by 6. This branch is also 11 R by 6. So when these two are connected in parallel, this will become 11 R by 12. This is 11 R by 12. And this one is 2R. Now these two are connected in parallel. Let's check the answer. So 11 R by 12 into 2R divided by 11 R by 12 plus 2R. This is R equivalent AB, right? If I simplify, here I can see 22 and here 22 plus 11, 35. Okay. So 22 R by 35 R equivalent we are getting. So final answer is 22 by 35, correct. Okay. So here first I saw there are resistors connected in series and parallel. I reduce maximum what I can do. I got this circuit, right? And as circuit have had input output symmetry, I easily open this branch or this junction, and as I opened this one, I got all series parallel, which we can easily simplify. Now let's see another example, similar example. So all the resistors are having equivalent resistance, equivalent resistance we have to calculate. All the resistors are of 12 ohm. What is the resistance between A and B? Okay. So between A and B resistor we need to find out. See, this circuit has got folding as well as input output symmetry. I already told any method you can follow. What you think is perfect for a given example, you follow that method and you can cross verify the answer by solving by another method, right? So across AB if I connect, so I can see folding symmetry as well as input output symmetry. So whatever current here, same as the current here, input output symmetry, and whatever the current here, same as the current here. So if this current is same as this current, there is no role of this resistor. Similarly, this current is same as this current, there is no role of this resistor. So as these two are not carrying any current, we can remove them from the circuit. Okay. And here look at this part, this is 2R, this is 2R. Okay. This is 2R, this is 2R, this is R, this is R, only this part is R, 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 3R. This 2R and 2R will make it R. R into 3R divided by R plus 3R, 3R by 4, 3R by 4 across AB, and this R is 12. Okay. So this will get cancel out 3. So answer is 9 ohm. You can solve this problem by folding symmetry, right? Now let us see next example. Again, now here there is no confusion, it is a clear case of input output symmetry, there is no folding symmetry. Okay, whatever current goes here, that means there is no current through this resistor. Okay, and then if you just look at the upper part, this one upon this one is equal to this one upon this one. I am getting Wheatstone bridge also. Okay, so as there is this one upon this one is equal to this one upon this one, Wheatstone bridge, there is no role of this resistor. So this I can remove and this I can remove. So if I remove this one, then I can see 4 resistors connected in series, 4R. Then here I can see 2 resistors connected in series, 2R. This is R, this is R. This one is 2R. Now 4R and 2R, they are connected in parallel. So for this parallel combination, 4R into 2R divided by 4R plus 2R, this is 8R by 6. So this is 8R by 6. Okay, that can be written 4R by 3. So this thing is 4R by 3. Okay, 4R by 3 plus R, 7R by 3 plus R, 13R by 3. 13R by 3. Let me check the calculation once again. So this is 4R. Okay, this is 2R. Okay, this one is R, this one is R, this is 2R, right? And here 4R and 2R, 4R into 2R divided by 4R plus 2R, 6 I can see here, 8 I can see here, 4 by 3 I can see here. This is 4R by 3, and now this R is connected in series. So 2R plus 4R by 3 will make it 6 and 10, 13. Okay, so 10R by 3, 10R by 3, 10R by 3, and this whole thing is 10R by 3. So upper one and the lower one, now these two are connected in parallel, right? So 10R by 3 into 2R divided by 10R by 3 plus 2R, 3 will get cancelled out. Here I can see 16 and here I can see 20. So 20R by 16 will give you 4 if you divide 4R by 5. So 4R by 5. Okay, so I hope this is also clear. So today we discuss simple input output symmetry and folding symmetry, and we also talk about Wheatstone bridge. So this whole discussion I hope is clear and you must have enjoyed the class.